Okay, so thanks everyone for joining us. Thanks Eduardo for joining us in this seminar. Eduardo Azevedo is a professor at Wharton, and he's talking about A/B testing. This is a 1 hour seminar, questions in between. So thanks a lot, Eduardo, for coming. And okay, so the floor is yours.
Okay, yeah. Por supuesto. Muchas gracias. Thank you so much for having me. It's a huge pleasure to, I've never been in person to Chile, but, I know you guys' work. And so as, a Latin American too, I think it's like really fun to be here and meet everyone, even if it's just on Zoom. And I'll talk about this paper about how to do experiments. So I guess let me move to my title slide. So this is called A/B testing with fat tails, and it's joint work with Alex Deng. So Alex is he's an industry job at Microsoft. Jose Montiel Olea, who is an econometrician from Colombia, or at Microsoft. They're economists who are researchers most of the time, who are all excellent. And I'll try to do like an hour or so. So, I think like doing more than that on Zoom usually doesn't really work out very well, but interrupt me anytime if you have questions. And what this paper is about is that experiments are increasingly important in a lot of different areas. The most prominent area where experiments are incredibly important is if you look at pretty much every internet company. So any major company, so like Google or Facebook, the way that they decide how pretty much every single innovation, whether it's going to be implemented or not, is that you have to run through an experiment. So if I go on Google right now, and if I search for Juan's website, Google is going to place me in like 10 experiments at the same time. And so, they're going to be testing like a better font, different search algorithms. And the way that the search engines work is that there's different parts of the search algorithm. So they're going to be fiddling with different parts independently. So, basically they use experiments all the time with millions and millions of people in each sample. And, it's like widely used, and it's seen as, this like huge productivity enhancement, because the way that you choose what's a good idea is not just that you see, hey, what's like the boss, what's like the most senior person think is a good idea. You have to actually test your ideas with real data and see what's a good idea. And it's widely seen as being extremely important for making all these products better, because it turns out that it's like really hard to find out what's a good idea. And so if you can actually run experiments, you can just do much better than if you're just guessing what's a good idea. And the other area is if you look at social science. So, since there's like a long tradition, but this has picked up steam recently of using experiments in social science. So if you take a field like development economics, the main methodology they use is to run experiments right now. And what this paper is about is how to optimally use scarce resources to do experiments when you want to learn about something to improve how you're doing something. So the model that we're going to consider is going to be like very similar. There's going to be a lot of details that are very similar to like what a major company like Google or Facebook, kind of like what's the problem that they face in deciding how they're going to run experiments. And this is like a very classical problem. So there's like in statistics and decision theory, there's like 100 years of literature of like optimal learning and how should you optimally gather data with scarce resources. And so what's going to be kind of like special about what we're doing is not going to be so much these details of trying to get this classical family of problems and set it up in a way that's more similar to what these internet companies are doing. But the biggest innovation in this paper is that we're going to not assume that the ideas that we're dealing with, they come from kind of like a thin-tailed quality distribution. Because when you look at this like 100 years of research about this, Almost every paper, either on purpose or like without paying attention, they pretty much assume that the quality of the innovations that you're trying to screen comes from kind of like either like a bounded distribution or like a thin tail distribution, like a normal distribution or something like that. And so, all the innovations are kind of like in the ballpark of like the same quality level. And what we're going to do instead is that we're going to allow, in principle, for the quality of the innovations to have like fat tails, to be so that, look, maybe there's like a few ideas that are like much better than other ideas and have like a much bigger effect. And then what are we going to find? The main result of the paper, the main like theoretical results, is going to be that, look, what you are supposed to do hugely depends on whether you have like fatter tails or thinner tails. And then, so that's like the theory part of this paper. And then there's going to be an empirical application that we worked with Microsoft to look at data from like metadata from all the experiments that they were doing at Bing, at the Bing search engine. And that's, I think when you talk about Bing, people usually laugh because, everybody who's attending the seminar uses Google and like never used Bing before. But Bing's like a real business. So Bing has like $7 billion of revenue per year. There's 600 million active users in the world. And in fact, maybe the most interesting thing that I learned doing this paper, there's in the United States, there's like 150 million people who use Bing. There's like 100 million people who use Bing and they don't use Google. So, maybe you never met any of those people, but they're definitely out there. And, probably Bing coming as the default has a lot to do with that. And so, we're going to just look at the data from the experiments at Bing. And indeed, we're going to find that the quality of the experiments at Bing actually seems to be very fat-tailed. Even though their practices are like they're like, before our research practices were like a little bit more consistent with what you should be doing in the thin-tailed case. So kind of like they run these very large, precise experiments. So like the average experiment in our data is going to have like 20 million users. And then a lot of our results are going to be saying, but look, if you're just like hunting for like these big wins, then maybe you could be running like a lot of little experiments that are not as high quality, and you have a higher chance of finding like a big win. So, I'll talk in the end of the talk, I'll talk about some of this like industry stuff and, like what practically you can do with this research. Yeah, so I think that's like that's like my introduction. And I guess, just like talking about Bing, I'll explain the graph later. I'll just try to explain this like without a graph right now. But this thing that I mentioned that like, when you look at Bing, the ideas seem to be very fat-tailed. So basically, the first time that I started working on this, when I met my co-author Alex Tang, I was asking him, so, do you think like most of the gains that you guys have come from like small innovations that people do? Or is it some like, big innovation? And he was like, oh yeah, most of the gains are like small effects because, almost everything has like a very small effect. And it's true because, since they can measure things so precisely, because the experiments have such a large sample size, they're hunting for like, small percentage improvements in like how well Bing's doing. But then he was like, well, of course, there's stuff like long ad titles. And so long ad titles is like a famous experiment at Bing that someone had the idea of increasing the length of the description of each ad. So, like when you search for something, you get shown like, 5 ads for like different things. And somebody had the idea of like, oh, let's make that string, instead of being like at most 30 characters, let's try to make like at most 60 characters. And then that, just like that one change, increased revenue on Bing by like 13%, increased ad revenue by 13%, and without like making any other metrics look worse. And that's like a lot because if revenue is like $7 billion per year, and you tried this one like silly idea and then you increased revenue by like 13%, that's like a very good day. And it's not like this like a super complicated idea. So the person had this idea, they had this idea, and it's like trivial to implement, but nobody did it for months because everybody thought it was like a bad idea. And then it turns out that, hey, if they go and they try, then, they get like this huge effect. So basically, what we're going to see in the theory is that how you should be running experiments is going to be hugely dependent of, you know, are you like trying to hunt for this like big wins that nobody knows what's a good idea, or are you trying to do a lot of like little incremental improvements? So it's kind of like, you know, what the theory is going to show, and they will like apply to this Bing example. All right, so my roadmap was that I was going to give an overview of the theory, and then talk about like little details of at Bing, how they do this, and then talk about like empirical analysis with the Bing data. And I feel weird because nobody's interrupting me, but so, you know, feel free to interrupt at any time. And with that, I was going to start talking about the model for this paper. The whole model is just one slide. So it's kind of like,
May I ask you
yeah, Ronald.
Yes, I was about curious because I understand that you can do this testing with this immense amount of data that you have, but normally for experiments more in the social sciences, like the more traditional experiments, you're not going to have that many data. So you're not going to be able to, I'm not sure if you'll be able to distinguish whether you are with fat tails or not, no? Or what would you advise for case in which you don't have 20 million, an experiment with 20 million users or something, but experience with a few thousand perhaps?
Yeah, no, that's a really good point, which is that like, you know, the theory part of this paper is kind of general. You know, I'll talk about kind of like what would have to be a little bit more restrictive when you look at this kind of like, you know, typical settings in like social science. But the empirical part is going to be very particular to this like, you know, super big company, like, you know, mega experiments. So it's like, you know what, I'll get there later, but it's like in my data, I use like 1,000 experiments, which is like much less than all the experiments that exist, but I just picked one kind of like more like pristine set of experiments that I like trust the data more. But so our data uses like 1,000 experiments. Each experiment has like 20 million users. So, you know, like our data is like for this paper, for like this one paper, our data is based on like 20 billion experiment users. So it's like, you know, every person on Earth was like in our data several times, you know, like to construct this data. Like the average person on Earth, you know, like was on this data several times. Now, you know, of course, it's like totally different from, you know, if I look at like a development, you know, economics experiment that sometimes have to randomize stuff by village, you know, and there's like only like 100 villages or something. So the theory is going to kind of like apply in principle to this. But you can't just like say like, oh, okay, look, they found it like in Wet Bing, you have fat tails, and so you should be moving towards this direction that, as you'll see, is going to be like a very wild direction that you want to kind of go nuts and like try like everything that you can try and run really bad experiments, and like, you know, it doesn't matter. So, you know, that's going to be kind of like the conclusion of like what you should do at Bing. But I'm not saying that you should do that in development economics. You know, I think when you take a different field, you have to do like a different meta-analysis, and it's gonna depend on, you know, what the meta-analysis shows. But the way that you go about the meta-analysis is like very similar, and so I'm like actually very excited to try to apply this stuff to other areas. That's kind of like a lot of what I'm doing now. So like tomorrow I have a call with like a company that they run internet experiments, but for like smaller companies instead of like, you know, a company like Google or something. So it's not gonna, you know, I think that population is like not gonna be like quite the same as trying to apply this to, you know, social science, but it's like getting a little bit closer. And I definitely want to go there. And, you know, I've been talking to people who do a lot of experiments in practice, try to see if we can help them do what they're doing like more productively, even by just importing Silicon Valley ideas into like, so, you know, the rest of science. So does that answer your question, Ronald?
Yeah, definitely.
Yeah, and you know, we can talk about more like, you know, as you start seeing the data, you know, at least after we understand the model, we can talk more. The data might not be very helpful because as you see, like the orders of magnitude are going to be so insane compared to like normal experiments that, you know, it's really not like informing, you know, what we should do like in our day-to-day stuff.
Eduardo?
Yeah.
I mean, how, I mean, you said that you have like 20 billion users or 20 billion, I mean, how scarce is really data? I mean, that's...
I know. So it's like, so this goes back to like, like the scale of everything being kind of like mind boggling, because we're like used to like small data sets in like our research. It takes a while to get used to like what's going on, to even understand like orders of magnitude. Like it took me a while, like when I was like opening this and downloading this to like develop my intuition. So I would say that for a business like Bing, having more data, having more users is the most scarce resource that they have. And then the second most scarce resource is engineer time. Now, of course, that's going to vary from business to business, but it's like pretty crazy to think about it that, like, look, these people have like, there's like one of the biggest shops in the world, and they would love to have like more data, for according to all my estimates, data is super valuable to them. And if you talk to them, clearly data is super valuable to them. And so kind of like what happens is that like when you have a bigger product that you have more users, sure, you have like, higher statistical resolution, but your statistical resolution only goes up with like square root of n, because, like standard errors are like all divided by square root of n and stuff like that. But then your revenue also goes up, and your revenue goes up kind of linearly with the number of users. So like the more data that you have, the more you want to like, hire more engineers and do ever like, smaller improvements. And then you kind of like always run out of data in the end of the day. And so data is kind of like always scarce.
Right. Yeah, no, I was also thinking about this idea that like information externalities in these companies, right? Like the idea that, Bonatti and, there are like a few papers like making the point that each of us is really like zero for adding zero for a company. But you seem to be suggesting contrary to that idea, or not?
No, people are like really valuable. It's like, so like the revenue that you get from a user. Well, I'm not sure if like, I think like the revenue is like, might be like a confidential number or whatever, but the ballpark people know because, I've seen like estimates on the internet of this, but the revenue per user for all of these companies is like, like $20, $50, something in that ballpark, maybe less than 100, let's just like give you like a ballpark. The value of the data just for running experiments is like 10% of that, so it's not like everything, but it's not zero, and this is just the value for running experiments that make your product better. So you can use data for all sorts of other things. So, yeah.
Eduardo?
Okay.
Yeah. I'm more used to experiments in retailers, so like in real physical settings. And in that industry, I think why people like fewer and large experiments, and I would say a priori two reasons. One of them is that they know that stores are very noisy, so they want to be sure that if it's something zero, it's real zero. But the second is that escalation is part of the problem. So maybe a good idea that works in 2 stores, when you try to implement it in 100 stores, is unfeasible. So that's why they want to run experiments in many stores, so they can have a sense if that is actually feasible when you want to escalate this issue. I don't know if that's part of the things you're going to talk about.
Yeah, I mean that that I'm not gonna have that in the slides. It's like in the paper we'd consider like a lot of different kinds of costs, and the kind of thing that you're saying is clearly gonna push towards like few big experiments. But I think that comes back to like the principles of like the theory are kind of like the same, but you can't just like take it and apply like the result to another setting. The result's going to depend on on the characteristics of like each setting. But anyway, like retail, it's like I think we should talk about this. That's like something I'm interested too. It's like can you apply Silicon Valley ideas to make retail experiments better? I don't know, but that sounds interesting.
Yeah,
maybe.
probably it's over here. If it's a good idea for one thing, it's good idea that you apply to million of other settings. So it's like constant return to scale for a good idea.
Mhm. Yeah.
Probably
Yeah.
what I'm
The retail is
thinking
not
is that
clear.
a good idea depends on the scale of implementation.
Yeah. Yeah. Well, anyway, so it's like, so that's, you know, this sounds like a very cool thing to discuss. Just so that I don't lose track, I'll try to first explain this like vanilla, you know, the like basic model, and then like the main idea of the theory, and then we can kind of move on. So, so the model that we have is like this. There's a firm, so it's kind of like Bing, and they have a set of potential innovations, I equals 1, 2, 3 up to capital I. So that's kind of like how many ideas per year engineers have to make Bing better. And then these ideas have some unknown true quality delta I. So that you think of that as like how many % better can you make Bing according to some performance metric of, you know, how good is Bing. And then we don't know the firm doesn't know the quality of that ideas. You don't know if it comes from a distribution GI. And you might as well consider the case where GI is the same. Consider the case where the ideas all come from the same distribution. An experimentation strategy is going to be a vector n saying how many experiments ni you want to put into idea I. So you could put 0 experiments in one idea, or you could put some higher number. There's a constraint that you only have some amount of data. So that's like, you know, how many users per year do you have that you can experiment on? And then each experiment with ni users is going to give you a signal, delta I hat, which is going to be normally distributed with mean equal to the true quality, and variance sigma squared I over ni. Once again, consider the case where sigma squared doesn't depend on I. So the, you know, the noise, experimental noise is the same for all ideas. And then the firm is also going to choose an implementation strategy S, where S is a set of ideas to implement, and S is going to be a random variable that's allowed to depend on the results of the experiments. So, you know, it's not like you can just like choose S to depend on the true qualities, because, you know, you don't know the true qualities. So there's like some restriction that S can only depend on the results of the experiments that you decided to run. And then the firm maximizes the expected payoff, which is just going to be the expectation of the sum of the qualities of the ideas that you implement. And then I guess the final math thing that I have to say is that sometimes in the talk, you're going to see delta and delta hat. You know, delta is the true quality, delta hat is the signal. Sometimes you're going to see them as lowercase letters. So basically, lowercase letter is going to mean a number, and then uppercase is going to mean a random variable. And so, but, you know, it's not like a different delta. It's like the same delta. It's just that, you know, we're going to be careful with like numbers and random variables. And then it's a great time for if people have clarifying questions, because we're just, you know, that's all all of our analysis is going to be about this model. So, you know, that's like the only theory we're going to do today. So if anyone has any questions, it's like a great time to clarify now, because you're not going to understand anything if you know, don't understand the basic model. Yeah, Ricardo. No question. Okay. All right. So let me just like talk about some, you know, some stuff that I've done here briefly. So one thing about this model is that it's not really dynamic. It's slightly dynamic because you look at the results of the experiments and then you choose what to implement, but that's it. And so that's going to be a little bit different from the literature on like bandits, for example. So that's a very prominent literature that, you know, the bandits literature, basically you can say very little about what you're supposed to do. You only have some like heuristics of like some algorithms that are good, and only in some very particular cases you can actually figure out what to do. So this is like, you know, a much more tractable kind of like model. It's also more similar to how this works in a real company, because basically at Bing, for example, and like at every other major company, experiments have to be run for a whole week, because there's a lot of day of the week effects. And so they want to make sure that the experiments work over the course of a week. So no, it's kind of like similar to the external validity retail issue that Carlos raised. And 1 week's a long time in real life. So they don't actually run that many 2-week experiments. So you can basically think of this as, look, you know, they run for a week. And you're not allowed to like stop in the middle because they were afraid of the engineers like stopping exactly when the idea is working. And so you have to kind of like, you know, commit to a length and like run it for that amount of time. The other thing is that like the payoff is just like the sum of the quality of everything that we can implement. And so that's basically because like in all these companies, there was like always like a huge debate of like, hey, should we just like do a lot of experiments in parallel, ignore all the other ones we're doing, and then just like, you know, do each one at a time and just like, you know, maximize that one, do all the analysis if that one is like a single one you're doing. That's like the parallelized approach. Or should we do like factorial experiments where we test like combinations of these ideas that you're doing? So, you know, there's like a huge debate every time that this company is like rediscovered experiments. You know, experiments exist for hundreds of years, but, you know, with the advent of like, you know, major cloud-based platforms, people rediscovered experiments because they're obviously such a good idea. And then they all had this debate of like, should we do factorial experiments or parallelized experiments? And then in every company, and you know, usually the people with a PhD were like in favor of factorial, but in every company, like, you know, they had like this debate, and in every company, it was obvious that parallelized experiments are much better because it's not that like interactions are like impossible, but they're kind of like rare. So for example, you know, the example that I like is that, you know, if someone's testing like a blue font on a website, maybe that looks nice. If somebody's testing like a blue background, that could look nice too. But blue font and blue background is obviously going to look really bad. And so, you know, sure, it's like possible, but these interactions are like kind of like rare enough that they have found that it's much better to just like ignore the interactions and run stuff like in parallel as much as you can. And so, you know, based on this like anecdotal finding that interactions tend to be small, we just assume the payoff is the sum. The other thing is that I'm making like the main scarce resource here, but they don't have enough data. You know, in this basic model, it's like the only scarce resource. So, you know, if you, in the paper, you see like when we prove our theorems that the key ideas, you know, they kind of work. You can like take the key ideas and, you know, put a bunch of other costs, and the other costs are going to matter for what you want to do. But, you know, the main analysis is going to be like, what are we going to do now? And I just chose this one cost here because it's like the most relevant cost at Bing. But, you know, you could analyze a bunch of other costs and that could be relevant in other settings. All right, so just, you know, so basically what are like the results that you get from this model? So the first result is that the optimal implementation strategy is actually easy. So condition on the experiments that you run, which ones you want to experiment is extremely easy, because basically what I'll do is that you look at the signals that you get, you use Bayes' rule to update how good you think each idea is. And if the posterior mean is positive, then you implement it. If the posterior mean is negative, then you don't implement it. So, you know, formally, if you denote, so there's a proposition saying exactly this. But one piece of notation that we're going to use is that formally you can denote pi of delta I hat and ni as being the posterior expectation mean of the expectation of quality. So it's, you know, using Bayes' rule and giving your prior and giving the signal that you observe, pi is how much do you think on average how good the idea is. So you just look at pi, and if it's positive, you implement the idea. If it's negative, you don't implement it. It turns out that because of the assumption that the error is normal, there's a threshold strategy. And so we denote the threshold signal as delta star I, and the threshold t statistic as the threshold signal divided by the standard error of the experiment, just like the frequency standard error. So, you know, this kind of like nice, it's just like saying like, you know, optimally the threshold t statistic, it's like what t statistic should you optimally ask for in an experiment so that you go and implement the thing? You know, should you ask for like 1.95? Should you ask for like a t stat of like 3? You know, that's like t star. So Jose, you have a question.
Yeah, sorry. So with respect about what you talked before, so in practice, different experiments need similar amount of users. or you have experiments that need a lot of users, and then some experiments need a few users?
In practice, it's similar.
So basically, it's more about the number of experiments you're doing.
Yeah, in practice, yeah.
Okay, because you said that you could also have a cost of an experiment, but maybe when you have a cost, not the user cost, but the cost of doing the experiment, maybe there's some changes that are very easy to do, have a low cost, like the change you said before, the description are longer, but then other changes can be much more expensive.
Yeah.
So maybe that variable is very important.
Yeah, no, absolutely. So it's like, one thing that's like, you can get a lot of interesting results about like, what kinds of ideas do you want to try to experiment? So it's like, if the more costly ideas, they have like more variance or something, do you want to do them? So
Okay.
that's interesting, but I'm not going to talk about it just like on this slide because I want to just like have a laser focus on the most important stuff.
Okay.
And, after you see like, the solution to the vanilla case, you'll be able to like by yourself have a lot of conjectures that are going to be correct if you look at the paper, for a lot of this stuff. Yeah.
What about the priors? What is the role of priors here? So there is always a prior such that you decide to go for big experiments. So like the manager, you mentioned that he never thought that there are black swans out there. So that's why they never try this.
Yeah. So kind of like the main thing that I want to do in the theory is that I want to establish relationships between the prior and what you want to do. It's like what you want to do depends on a bunch of stuff. Depends on the costs, which like in this basic model, I don't even have different kinds of costs and stuff like that. But one key thing that it's going to depend on is going to be the priors. And so, that's like basically what like the main results are. And then like everything else is kind of like is downhill from there. It's a kind of easy once you understand like how what you're supposed to depend on the prior. Yeah. All right. So here's like a really important definition for solving this. So define the production function of idea I as the net value of putting NI users into idea I. So it's kind of like how much money, how much percent improvement do you get in expectation by putting NI users in idea I. So this is sometimes called the value of information in the literature. There's like a big literature in value of information. And so basically, if I put NI users, so I'll just like walk through the definition. So if I put NI users in an experiment on idea I, how much I'm getting is, well, I'm going to run the experiment with NI users. I'll get our signal, delta hat I. And then if my posterior mean is positive, I'm going to implement that. And because Bayes' rule is right on average, the payoff that I'm going to get on average is going to be the expectation of the posterior if the posterior is positive. So, the total value that I'm getting from having NI users and having idea I is this expectation over here. And then I'm subtracting the value of having idea I and not running an experiment, which is the average quality of the idea, if that's positive, because I can just implement it by default without even looking at any data, and 0 otherwise. So this is what we call the production function, and the literature sometimes calls the value of information. It's just like the value of putting NI users in each idea. And then what's nice about this production function is that now you can see how this problem is basically like neoclassical producer theory, because you just have like a total budget of capital N users, and you only split it through your ideas in the most productive way possible. So there's a little proposition that's an account in the composition, which is saying that if your implementation strategy is optimal, then the expected profits are the value of having the ideas and having no data. So the sum of the means of quality, if they're positive, plus the sum of the production functions for each idea, evaluated how much users actually put in each idea. So you just want to maximize the sum here. And so that's why everything is going to depend on the production function. So typically you're going to have that like with increasing return to scale, so kind of like convex production functions, you're going to be in the case where you want to run like a, you want to like abandon most of your ideas, choose a few ideas that are like the most promising, and run like a few big, very precise experiments. And then with kind of like decreased returns to scale, it's going to be the opposite, with like a concave production function. You want to go and you want to run just like, like a lot of experiments, and like push the limits until you find like some other cost that's going to matter and it's going to like bind eventually. So great. So the point of this is like, okay, so once I write this down correctly, it's all like, classical producer theory, and everything depends on, the shape and like, magnitudes and stuff. And, at a more coarse qualitative level on the just like, returns to scale of this production function. So it's kind of nice. So, we had like a potentially difficult problem that now we see that it's actually pretty easy. And so the whole game is going to be to relate properties of the prior to properties of the production function. And because, we can like do a bunch of examples in the computer, it's not that hard to go and do this. So let's go and do this next. So, let's just like go on MATLAB and do a bunch of examples and see what we're going to find. So this is a slide that's doing exactly that. So here we have size of the experiment. So in my slide, it goes from 0 up to 40 million people. And then what I plotted was for some normal prior, call this like an illustrative normal prior for now. This is the production function. I'm actually dividing by f of infinity by the value that you get with perfect information. And you see that, look, for this normal prior, I'm getting like a very convex production function. I mean, of course, eventually it has to become concave because you can't get more than 100% of the value of perfect information. So eventually it's going to be concave. But at least for this range that we plotted here, you see that you get like, this like very convex production function with like very increasing return to scale. Now, here is a bunch of pictures with t-distribution priors. And the t-distribution is a distribution that kind of looks like a normal distribution, but it has fat tails. And the t-distribution has an extra parameter, which is called the Pareto tail parameter, alpha. And the lower alpha, the fatter the tails. So for example, if alpha equals 2, the variance is infinity. If alpha equals 1, the mean is infinity. So the lower alpha, the fatter the tails. And then when I do plots with the t-distribution, I see that, hey, look, interesting. If I start with like a relatively big alpha, so relatively thin tails, I get a similar shape as in the normal distribution case. But then as I lower alpha, I start getting this totally different shape that eventually becomes like super concave. And so, eventually as you get like fat tails, you go from having this like increasing returns to scale to having very decreasing returns to scale. So basically what you're supposed to do if you have like fat tails or not is like totally different. And then, basically what's happening here. So in a nutshell, what's happening is that if you have sufficiently thin tails, then what you're doing is you're trying to do kind of like a bunch of incremental innovations that are like the same size. And then running a really small experiment isn't very helpful because, for example, if your prior mean is that if your prior said the mean's negative, so by default, you don't want to implement anything, you have to get like very good news in these small experiments to actually change your mind and decide to implement the thing. But if you're running like a super noisy experiment, it's like very unlikely that you're going to get such good news. Now, if you have this fat-tailed case, it's very different because, you're basically like hunting for kind of like the long ad titles idea that it's like this rare big win that you almost never get. But if you do find one of those, even if you run a tiny experiment, it's going to be just like so significant because it's such a big improvement that you're still going to find it anyway. So what you want to do is that you want to run like a lot of pretty imprecise experiments. And sure, you're not going to be able to tell the mediocre good ideas from the mediocre bad ideas, but you don't really care because you're still going to be able to find the like big home runs that it's like, really what's like driving most of the payoff. So it's kind of like what's happening here. And another thing that's happening here is that if you squint a little bit more, it turns out that there's a magic number, which is alpha equals 3. So when alpha goes from being bigger than 3 to smaller than 3, that's when you move from convex to concave. And so, it's like a magical movement because like on average, you're still gonna get like an intermediate, degree of like how steep, how decreasing the returns to scale are when you cross like alpha equals 3, but alpha equals 3 is like, the theoretical magic number where at 0, this thing switches from being convex to being concave. And so now that we like, numerically figured out basically what's going on, I would just state the proposition for what's going on. And so let me just skip some like introduction about fat tails, just go over the main assumptions for this paper. So let's say that every idea has the same quality distribution. Let's say that the mean is finite and negative, and it's minus m. Assume that the right tail is asymptotically a power law. So power law is just a particular kind of very famous fat tail distribution. So it's like, income distributions, for example, look like power laws. And what a power law means is that the probability that quality is greater than delta is approximately proportional to some constant times delta to minus some power alpha. And so alpha is that tail coefficient that I mentioned. So, alpha equals 1 would be infinite mean case. Alpha equals 2 is the infinite variance case. Income distributions are like alpha between 1.5 and 2. So that gives you like, a sense of alpha. And the only formula that we really have to use for power laws in this paper is that the expectation of quality, and by the way, tilde is notation for asymptotically equivalent to. That means that for large delta, the ratio of the two sides converges to 1. So, you see tilde in a bunch of places. And if you're not used to this kind of math, you can just think about, approximately the same. Now, the only formula that we're going to use is that, and I think it's actually kind of like a nice formula to even understand what power laws look like, is what's the conditional expectation of quality? Conditional quality being greater than some value delta. And the formula is that it's alpha divided by alpha minus 1 times delta, times the threshold. And so this is actually a very nice formula to see how power laws are so different than like the normal distribution. So take like, wealth. So for wealth, this formula would be like alpha is like 1.5. So there's like 1.5 divided by 0.5. So 3 times. So it's saying like, if I take someone very rich, like Shaquille O'Neal, the average person who's richer than Shaquille O'Neal, they're 3 times richer than Shaq. But, it's like very different than the normal distribution, which is the distribution of height, because the average person who's taller than Shaquille O'Neal, they're not going to be 3 times as tall as Shaquille O'Neal. They're like, a little bit taller than Shaquille O'Neal. So power laws really have this, like kind of like extreme observations. And then the main theorem in this paper is explaining what the production function looks like when n is small. And the theorem says that this is going to say 2 things. So there's like some formulas that I'm not going to go over like the details of the formulas, but the first one is going to tell you what happens to the threshold t statistic. And basically it's going to converge to infinity, but it's going to converge to infinity like extremely slowly. So, it's going to converge to infinity, but like in practice, it's going to be like 3 or something, or like, 2.5. And, I'm not going to go into details of this formula, but you can see how it has like a log of sigma over square root of n. So, when n becomes small, so that your experiments become very imprecise, even if the standard error of the experiment, sigma over square root of n, even if that's growing a lot, log of that is not going to grow like crazy. And then second, the marginal products are proportional to about n to the power alpha minus 3 over 2. And so, I'm not going to like go over like the constant, but basically you get that, the marginal products are proportional to something that doesn't depend on n very much, times n to the alpha minus 3 over 2. So that's kind of cool because it's saying that, look, the marginal product at n equals 0 is going to be infinity when the tail is going to be sufficiently fat, alpha is smaller than 3. And the marginal product at 0 is going to be 0 if the tails are sufficiently thin. So not only like it switches from convex to concave, but it switches from like infinite marginal product at 0 to like 0 marginal product at 0. So yeah, that's like the main result of this paper. And it's basically kind of like giving like a theoretical explanation for why, you know, like we see the patterns that we see in the data. And it's saying exactly the kind of thing that, you know, small alpha, you want to have this like lean experimentation strategies that like try everything. And big alpha, you know, you want to have this like, you know, big data experimentation strategies that do like a small number of like very precise experiments. And of course, like, you know, having other stuff like a fixed cost of an experiment and, you know, other stuff like that, changing the noise, it's going to change all these conclusions. But this is just basically saying like thin-tailed priors push you towards a few big experiments, and fat-tailed priors push you towards a lot of really small experiments. I'm not going to explain like corollaries that we have in the paper, like formalizing this. You know, it should be clear enough that, you know, how like once you prove this theorem, you get a bunch of results like that. Now, here's some intuition for why 3 is the magic number. And then I guess I'll switch to talking briefly about the like some applied stuff, because I think you understand the theory a lot better if you like see it in practice. So imagine a startup that follows a lean experimentation strategy. So they try a lot of ideas with small sample sizes. And they only implement outlier ideas that have a t-statistic of 4 or more. So, you know, it's not necessarily optimal to do this, but it's just like what they're doing. They're doing this like, you know, crazy strategy of like do a lot of small experiments and only implement stuff that has a huge t-statistic. Well, so innovations that have a quality of, let's say, 7 standard errors above the mean are definitely going to be implemented. So their production function should be, you know, approximately, let's just take a heuristic of only considering those ideas being implemented as being like the good ones. So the production function is going to be the integral from delta going from 7 standard deviations above the mean. So, you know, though all these innovations have this such a high quality are going to get implemented up to infinity of delta times g of delta. But this is just going to be the probability that there are ever 7 standard errors above the mean multiplied by the expectation of delta, conditional being 7 standard errors above the mean. But then the conditional expectation is just a Shaquille O'Neal formula. So it's going to be alpha over alpha minus 1 times 7 standard errors. And then multiplied by the probability that there are 7 standard errors, you know, in the tail. And that's going to be, because this thing's asymptotically a power law, then this probability is going to be, you know, 7 standard errors to the power of minus alpha. And so I'm not going to do all the algebra here, but then if you do it, you're going to find that the production function should be approximately equal to the n to the alpha minus 1 over 2. So if you take the derivative, you get alpha minus 3 over 2. So I think that's like the easiest like intuitive argument that anyone could do in a piece of paper. You know, you could like after the talk on your scratch paper and you could remind yourself, you know, of like, oh, what's a magical threshold? It's 3. And, you know, you can calculate it that way. Now, it's not very satisfying because it, you know, it kind of like looks like it's not going to be like, it looks like so heuristic that this could never be built up into like a real proof. But then it turns out that, you know, once you work it out the real proof, it's like surprisingly similar to this argument. So I'm not going to do like the real proof, but basically, you know, the way the real proof works is that you have to realize that it's like, if you're like at the threshold, you know, imagine that you see a signal that's exactly like the marginal signal. So let's say that delta star n is, you know, like the threshold signal that you would see that you decide to implement something or not. That means that when you see that signal, your posterior expectation of quality is 0, but your posterior is going to be the product of the normal noise centered at the signal that you observed and the prior g of delta. So it's going to be the product of like this red curve and this like blue curve here. But then the blue curve, as you are getting the case of close to the case of n equals 0, the experiment becomes really noisy. So the blue curve is basically becoming like a flat curve. So you have to, like, as you move towards like, you know, very low noise, the blue curve has to be moving to the right, because if you didn't move to the right, then you just see like a flat blue curve, because, you know, like delta star n would be like kind of like stuck close to 0, and the blue curve is getting flatter and flatter. And so when you take like the average of something, with like the red curve multiplied by a constant, you get like a negative mean. So that would be impossible because at the threshold, you're like indifferent. But then the blue curve can't be moving to the right too fast, because since this one's like a normal distribution, that it becomes extremely close to zero at like an exponential rate, whereas the power law gets close to zero much slower because it has like these fat tails. So it's kind of like the threshold signal has to grow, but it can't grow too much. So it's like the threshold signal is going to infinity, but it's not going to infinity too much. And so what that's going to do is that, like, in the end of the day, your posterior is going to look a lot like a step function when you have like a very small n, that it's kind of like below the threshold, you like never want to implement something. And then above the threshold, you want to implement it, and you kind of like take stuff at face value. And then you get like an integral for what's the value that you're getting out of that, which is basically the same integral that we had like in the heuristic proof, except that when I had like 7 standard errors, I'm going to have some, expression that depends on the t-statistic, and it depends on a bunch of stuff. But, because it's like going to infinity, but it's going to infinity kind of slow, it's going to kind of, work out that you get the, the exact formulas in the theorem. So it's like, you can see how it's like a bunch of analysis. And, fortunately, one of my co-authors, like, not only a really good econometrician, but he's also a really good statistician. So, he like saved this. But, the basic idea is like, if you just take the heuristic arguments and you like do it a little bit nicer, then it kind of works out. All right, so that's what I said about, yeah.
Eduardo, like, it seems, I might be wrong, but probably I'm wrong, but it seems to me that the result, I mean, this basic intuition about how you should organize experimentations should apply even when n, I mean, sort of regardless of n or not.
You mean whether it should apply to like development economics or something?
Right, exactly. Or no, I mean the theory. I mean, like the idea that you should run like lean experiments. I mean, when they fail, when they fat, it should apply regardless of n, right? Or I mean, but or not.
Yeah, I think so. I mean, and I think like the only assumption that I used that is like better with this internet stuff is that I assume that the error in the experiments is normal. And so, for internet stuff, that's obviously a very good assumption because of the central limit theorem. But for some social science stuff, you have like 100 villages. Do you want to assume that the error is normal? Maybe.
Mm-hmm. Right.
But otherwise, I think this makes sense. And it just like also makes so much intuitive sense that, like one way to like criticize my paper is like, look, you did all this stuff just to say that like, if you're like fishing for like very big wins, then you want to go crazy and fish for very big wins. And if you're looking for mediocre stuff, you want to, do very precise experiments. So it's like, it's like once we see like the conclusion, it's also like not rocket science. So I think it kind of like, it's just so intuitively that it should kind of like apply more broadly. All right, so I'll talk a little bit like in the end of the time. So I wanted to finish in 1 hour. So should I finish in 1 hour, 10 minutes, or should we just do it a theory talk and like finish?
No, I mean, I think we still have like 10 minutes. I mean, that will be fine. We started at 12:05, so I think we should, I mean, we still have 10 minutes, so that's fine.
Okay, so yeah, that's all good. So I'll try to like in 10 minutes give like an overview of like what they do at Bing, and then what happens when you apply this model to the data. All right, so Bing has an experimental group called EXP. So they actually used to be part of Bing. They're not part of Bing anymore. Now they run experiments for a lot of other parts of Microsoft. Like if you go on Word, you're also being experimented on, it turns out. And EXP engineers are going to run the experiments on you. And it's just like kind of like an ideal data set to study this because we have detailed data on thousands of experiments per year. We have, one of the best experimentation infrastructures in the industries. It's kind of like a big business of independent interest on its own. There's a lot of issues with like validity of the observations in that some of the observations in the data, they're just like wrong. It was like some bug. So we actually had to have like an RA, like manually call people and like track down which things are like real things. So I'm going to skip how that was done, but it's like, even taking this kind of like ideal data set for this research, it's actually like the nitty gritty of having a reliable data set is like pretty hard. And, you know, we did our best. We went to the nitty gritty, but it's important. This is like what a typical experiment looks like. This, you know, this one, this is like an ad. And so they try like, you know, hey, do you want to have like ads with underlines or without underlines? And then this from a training deck. So they get people and they ask them like, hey, which experiment do you think is better? You know, which variation do you think is better, this one or this one? And people like raise their hands. And then the point of like doing this is that like almost nobody can guess like 3 of those correctly. So it's like extremely hard to predict what's gonna like work in practice. So their philosophy is like, look, you should have like a uniform prior over like every idea, and you should test everything, and should never like implement something just because some, you know, some like rich person thinks it's like a good idea. This is what like a dashboard looks like. So the engineers have access to this like dashboards where they see, so session success rate, that's like the main metric that they use. That's you just track the clicks of everyone who's like in the experiment, and you see whether it looks like they found what they were looking for. So it's kind of like if you go on Bing and you search for cats and you click on the first page and you stay there, that's considered a success. If you don't click and search for something else, that's considered a fail. If you click, but you immediately go back and click on something else, it's also considered a fail. So there's some stuff, basically everything you do on the internet all the time is being tracked. And, you know, that's being used to calculate the session success rate. The experiments that we're going to consider in our analysis are all going to be interface and like search algorithm experiments and stuff like that. They're purely focused on the user experience, and they don't care about revenue. And, you know, so that's nice because session success is like the main metric that people look at to decide whether they want to implement something like that. Even though there's like many other metrics, you know, there's like thousands of metrics that get recorded. And for privacy reasons, like the detailed data of everything that you get done on the internet, that gets deleted automatically every 3 months. But it's okay for you to record for every one of these thousands of experiments, thousands of metrics, you know, aggregated at the experiment level, and at the level of like demographics and stuff like that. So that's the data that we use to do this paper. So it's kind of like, it's like a small data paper because like, you know, the data set itself that you start with is like this petabyte scale data set of all the experiments. But in the end, we're just gonna have like a small table that has like 1,000 experiments and what's like the effect size and what's the standard error and the sample size for like each one of those experiments. We use a little bit more than that to do some like fancier analysis, but you know, that's like basically what we use. And then, you know, here's like an example of like one of those outliers. So this is the long ad titles experiment that you can see that it increased revenue by 13.41%. You can see how precise the estimates of revenue are. So it's like, you know, they can estimate revenue with a standard error of 0.06%. You know, that's because if you have on average 20 million people per experiment, you can estimate stuff really well. But, you know, this one, the gain was like 13%. So, you know, clearly you don't need to have such a good experiment to detect this. And this kinds of ideas, you know, like long ad titles, that's like, you know, what inspires, they have like a bunch of war stories like this. And that's what, you know, inspires this philosophy that they try to treat all ideas as being like the same and coming from the same prior. All right, so, you know, what did we do? And by the way, this is like, they do a bunch of like offline triage of ideas. So you hire a bunch of people in China to look at side-by-side search results of like this. And then only the ideas that do well enough in triage or don't appear horrible in triage actually go to an online experiment. So it's kind of like, you know, they have like a bunch of ideas that never get used. You know, a bunch of stuff gets like thrown out in triage, or they used to have them. And we have some data on these ideas that get thrown out, but, you know, I'm not going to talk about those too much. All right, so I'll skip like, you know, the exact data construction and stuff like that. And like summary stats, I'll skip. So I'll just tell you instead of showing a bunch of tables. So basically the summary stats, you know, you can see like, look, the average size of an experiment is like 20 million. the average, like, effect size they look for, like the super small effect sizes. So here's like a nice picture. Here's like a very important picture, which is like, if you just do a histogram of delta hat of, what was like the estimated effect sizes they have found when all the experiments they've run, then you see that, look, it's like concentrated at 0. This is like the improvement in session success rate, that like main performance metric of like how much better Bing is doing. And it's like very small. It's like this is like 0.2% improvement in session success rate because everything's like so precise. But there's all this dirt over here. So if you're like used to looking at this, it's just like very obvious that it's like not a normal distribution at all, that there's like this fat tails. And then there's a bunch of like formal tests and other descriptive stats that you can do. So I'm going to skip that in the interest of time, but you can do what's called like a log-log plot to try to see if there's fat tails. And it's just like very clear that there's like very fat tails here. So if you actually do the estimation, which I'll skip to, so this is the only number that I'll talk about, which is like our like baseline estimate of the tails, and it's like 1.32. And so, we find that the tails are pretty fat and well below the alpha equals 3 magical threshold. And we know the confidence interval is like well below alpha equals 3. There's a bunch of like robustness and other stuff that in like placebo analysis that I'm not going to go over. But you can look at the consequence.
Eduardo, may I interrupt 1 second? 132 was below 3, no? So it should be convex.
It's
function. Am I wrong?
So it's concave. It's concave below 3. Yeah,
convex below 3. Okay.
And so, just so I guess I'll finish with like a plot of the production function. So where's the production function? Oh, actually, yeah. So this is like what the production function looks like. So you can see how it's like, super concave in practice. And then the main, like, there's like 2 main applied conclusions that you get out of this that, it's in the paper. I'm not going to go over, like, there's some pretty graphs about this. But one is that because of the fat tails, the way that you judge ideas has to like completely change. Because if you draw a graph of that P function, the function of like, how good do I think an idea is given the result of the experiment, basically what you want to do is that when you find an idea that's kind of like mediocre, that the effect size is like, a t-statistic of like 2 in the experiment or something like that, you want to shrink that very aggressively towards 0, because since you're like running thousands of experiments and most of them are like not very good, then, when you see something with like a t-stat of 2, probably you just got lucky. So, it's like if you think that that's like a plus 0.1 improvement, actually that's probably like a plus 0.01, on average or something. But then when you see like a big outlier, those are like real. You don't want to shrink those at all, because since the errors are normal, there's like no way that you could have gotten a t-stat of like 4, if just because of experimental error. And indeed, like in the data, there's stuff that has like, a t-stat of like 20 or something. So those you don't want to shrink. Those are like real. And then the other thing is that all this like triage and stuff like that they used to do, it's like you shouldn't be doing any of that. It's like, because what it seems to look like, it's like it's really hard to predict what's a good idea. And you get a lot of the gains from big outliers. So running smaller experiments is not like a big cost. So you should like eliminate to the extent that you can all those like triage procedures and stuff like that. And indeed, like the limited evidence that we have of like the ideas that like we try to like take ideas that we have that on like their triage performance, and we see like how well they performed in triage and how well they performed online, and there's like basically no correlation. So it's also like indicative of that. And then that's what I had. And then more generally, I'd say that like we talked about before, I think what this paper is doing is like taking these companies that are like the biggest market cap companies in the world and trying to help them make a little bit more money, which is not like the most socially valuable thing. I think those companies are doing fine at making money before MIPP. So I think like the most interesting direction of this research is, not only like understanding what they're doing and helping them do it a little bit better, but it's like, what are like other areas that are like more socially valuable that we can take lessons, both from our research and just like of other things that these companies are doing, and apply them to other areas. So thanks a lot for all the questions. And, this is like really fun, and I'll be happy to hang out for longer, even though I want to keep people longer. I see that Ricardo has already his hands up. So
Thanks, Eduardo. I don't know if there is any question or comment.
Yeah.
Well,
Carlos.
go ahead, Professor Norton.
Okay.
Please.
Eduardo, I was thinking about this, that you have symmetric distributions, right? So you can have black swans and really stupid ideas. And I was wondering if that's part of the theory. Do you need that? Because in some sense, we have no clue. So sometimes you are going to try very stupid things. Or maybe you can think, well, in reality, I can figure out more or less what are really stupid, bad ideas. And therefore, it should be somehow skewed towards good ideas. I mean, I may have zero or positive impact, but I somehow I can, censor the really stupid ideas, like put the ads in a different language, or I don't know, in a tiny font or something like that.
No, that's a really important thing, actually. So basically, what matters, my theorem statement was a little simplified. So what matters is what's the tail on the other side of the default. So for example, at Bing, the average idea quality is negative. So at Bing, as a default, you don't want to implement stuff. And so in that case, what matters is the right tail.
All right.
And in the case where the average is positive, so as a default, if you didn't have any data, you would want to implement stuff, then the tail that would matter would be the left tail. But I think, for most, for every other company that I've seen, similar data sets. So for example, there are some people at Facebook that they have a paper, talking about some similar stuff to what we do. It's very cool. Trying to do this corrections for, if you look at an experimental result, what's how much should you shrink that? In that case, the mean is also negative. And, I'm not familiar with that many, companies, but people that have approached me and that I have seen what they're doing, the negative mean case is very common. And so it's the right tail that matters in that case.
Right. So is the fat tail, what matters is the fat tails of the good ideas.
The good ideas. Yeah.
The fat tail of bad ideas are not critical for most of your results.
Yeah, they're critical in the case where the mean is positive, but I don't think that's a very common case. But I don't know. It's not like I've seen every company, what they do. So. And maybe for other areas, the mean is positive too, because if you look at my friends who are in kind of behavioral economics, they're all trying to come up with these interventions for getting people to save more and whatever. And their papers always work out. So I don't know, maybe their means are positive.
Yeah, I mean, I was thinking when you have in Bayesian econometrics, when you want to say I have no clue, it's you have flat, right? Flat priors, and that cover a lot of bad ideas. So in some sense, when you do have this I have no clue assumption, you are then basically having fat tails and including a lot of bad ideas. So so that might or might not be realistic. If you think if you ask managers, they're going to say, "Oh no, I can distinguish a bad idea when I see it." Mm-hmm. Definitely, it's I don't know. Arguably, it's hard to say in advance.
Yeah, I mean, there's also other stuff in practice, for example, experiments that are really bad, they get stopped automatically after a few, samples, because that happens pretty often because all the time you're trying something new and you introduce some bug that the page doesn't load at all or something. So those things get detected, and after 200 observations, they get shut down. So so I think if you include something like that in the model, some kind of system like that, maybe you should yeah, I mean, I don't know how I would include that in the model, but in principle, that's one example of why it's important to understand which tail matters, because otherwise it could change. Ricardo.
Yes, thank you, Professor Azevedo. My question is whether the design of the experimental design can have its effect on the parameters. For instance, I've seen that with the experiment conducted at Bing, underlines wins, but if I were a subject, I would say, well, perhaps blue is not, it's not an hyperlink, whereas underline I would interpret as underlinks, and once it is an hyperlink, I would be incentivized to click on it.
So what's your question? ¿Cuál es la pregunta? Yo solo no comprendí cuál es la pregunta.
No, whether the experimental design can affect the parameters of the experiment, like that. No, nothing, because the underline, ¿puedes decir en español, por favor?
Sí, vale, como quiera.
Lo que pasa es que cuando en ese experimento, cuando aparece subrayado, yo podría suponer que subrayado es se podría que es un hipervínculo. En cambio, que lo que no está subrayado no lo es, de modo que por esa razón hubiera preferido uno que sea subrayado. Por esa razón la pregunta de que si acaso el diseño del experimento puede afectar los parámetros de este.
Ah, sí, por supuesto, porque en el dataset, cada experimento es una idea que un ingeniero tuvo. Y como esta, por ejemplo, una idea así como esta podría estar en nuestro dataset. Esta en particular no está porque es un experimento de revenue, que es diferente de los experimentos de user experience que nosotros estamos usando. Pero la calidad de la idea es la calidad de la idea que el ingeniero tuvo. Y por supuesto que una área que es importante también, que las compañías pueden mejorar también cosas, es que cuando usted tiene experimento, usted cambia el tipo de ideas que está intentando. Porque, por ejemplo, sin experimento, una idea que probablemente es mala, pero que puede ser muy buena, usted no la debe intentar. Pero si tiene experimento, es muy bueno intentar ideas que son así ruidosas, que no se sabe si son malas o buenas.
Muy bien, eso era todo, profesor Azevedo. Muchísimas gracias.
Gracias, Ricardo, por la pregunta.
Okay, so thanks a lot, everyone, for joining us. Thanks, Eduardo, for joining us too and giving this very interesting talk. Virtual clapping, I think.
It's all good, yeah.
It's due. And thanks a lot. Thanks a lot.
Yeah, no, thanks. It's really fun to, and feel free to email me if you guys want to chat. Carlos, I don't know if you have any retail partners that, are like doing a lot of experiments. If you want to chat, I'm like very interested. We have like students working on similar stuff. So
we definitely,
it's very, very good to meet everyone. Very cool coming.
Good, thanks.
Excellent. Thank you.
Bye. Thank you. Gracias. Ciao.
You're out.